Today's topic is motion detection in machine vision. Motion detection has many useful applications in robotics, especially because motion can often be a key that indicates a direction in which your robot should look to get more useful information about what's happening around it. Many times, motion is an indicator of where interesting things are happening. This is often true in security kinds of applications, search and rescue, and most applications that involve interactions with humans. We're going to be looking at two different types of motion detection approaches. The first is called motion by difference. Motion by difference is similar to background subtraction, in that this method involves subtracting one image from another. Motion by difference has the advantages that it is a simple and fast method. However, this method has the drawback that it only indicates the locations where motion is occurring. It does not tell us what the actual velocity is of any given pixel. The second method we'll be learning today is called optical flow. The optical flow method is similar to the masking method that we've learned previously. In contrast to the motion by difference method, optical flow is computationally intensive. It can be slow and require lots of power. However, this method will give us not only the locations where motion is occurring, but it will also tell us the velocity, that is, the speed and the direction of motion of each pixel or each object in the image. Now, in order to start thinking about how motion detection works, we have to do a little bit of thinking about dimensionality. Dimensionality is a word that refers to the number of different kinds of information in a data set. When we're talking about dimensionality in the context of machine vision, dimensionality refers to the number of different kinds of information in an image. Let's focus on one single pixel. And let's try and think of all of the different kinds of information that we get in one pixel. Some of these kinds of information we've already used in other image processing approaches. For example, we have the red intensity, the blue intensity, and the green intensity. These are three different kinds of information contained in a single pixel. But these are not the only three dimensions that a pixel has. Each pixel also has an X location. That is, which pixel is this pixel in the left to right or X axis. Each pixel also has a Y location. One last dimension that each pixel has that we haven't yet used in any of our image processing approaches is time. Every pixel and every image that we take not only has color and XY location of a pixel within an image, but we also have a time at which that pixel was captured. Motion detection approaches exploit the time information in pixels and images to evaluate the changes that occur through time. It will become more evident what this means as we go through these two motion methods, motion by difference and optical flow. I'm going to give you some of the theoretical background of this method first, and then we're going to set up motion by difference in our Python code, and we'll do a little bit of experimentation to see how well this works. Motion by difference is very similar to the background subtraction method that we learned previously. The only difference is that instead of capturing one background image, which I continue to use for a long amount of time, in motion by difference, we continually capture a background image and a foreground image that are spaced in time by some delta t. In other words, the flow of this method works like this. Capture a background image, wait an amount of time, delta t. Capture a foreground image, subtract one of the images from the other, and then display the difference. We also have to include some surrounding code to make sure that none of these pixels end up being negative and that none of them end up being larger than 255. Although this method is very simple, you can do a little bit of adjustment of how well it works and what kinds of velocities of moving objects you can detect by adjusting this delta t value. Let me give you a little illustration of that. Suppose that your first image matrix looks like this. I'm going to write a very low resolution image just to make the math faster to do. Also, I'm going to assume that this is a black and white image, although the actual image that we implement it on will be grayscale. So since this image is black and white, its pixel values are either 0 or 1. So this image matrix represents an object located in the upper left-hand corner. Let's suppose that this object is moving across the screen. If this object is moving across the screen, then after I wait an amount of time delta t, I'll get a second image like this. In this case, let's suppose that delta t is small. Now, suppose that I take the second image, subtract the first, and then make any value that is less than 0 become 0. What will the resulting image look like? After subtraction and limiting, that is, taking any values that are less than 0 and making them equal to 0, the image that I get looks like this. If I would then use our center of mass approach to find the center of location of this object, I would find the object here between the first and second rows and directly on the third column. Now, let's suppose that instead of a small delta t, I use a larger delta t. I'll call this a medium delta t, and we'll quantify this a little bit more in a moment. Since we have a larger delta t, the object has moved farther between the first picture and the second picture. So now what will happen after subtraction? In this case, after subtraction and limiting, we get the image as shown here. What's the difference between the right image and the left image? The image on the left will show a brighter image of the motion because here we have 4 pixels of motion representing the object, and on the right we only have 2. That happened because in the right example, delta t is small enough that the object overlaps itself between the 2 images. This would suggest that a higher delta t is better. However, there are several things that you have to take into account when you are choosing a larger delta t. One thing you have to be careful of is not to set delta t so high that the object will actually move all the way across the screen and off the screen before you get the second image. Also, the delta t value that you choose for this detection determines your sampling rate of the motion. For example, even if you set delta t small enough that the object does not move all the way across the screen and off the screen in the time allotted. If you set delta t to be too high, then you may only get a few samples of the object's position as it moves across the screen. One of the reasons that this is important to keep in mind is because one of the applications of motion detection is motion tracking. For example, we may want to have something rotating and pointing at the object that's moving while this happens. The slower or lower our sampling rate is detecting the motion, the more difficult it will be to be able to control the motion of the thing that is rotating towards the thing that is moving during this time. We would like to set delta t in such a way that we can brightly capture this motion and also get as many samples as possible as the object moves across the screen. Let's take a look at how we might estimate a good value of delta t. I'm going to start by estimating the velocity of the object in units of pixels per second. It actually doesn't matter that this velocity is in pixels per second. You can use a velocity in any units as long as all of the units you're using agree. But it's a little bit hard to picture in your mind why this is true. It's easier to understand how this derivation works if you assume that it's in pixels per second. So I'm going to start by assuming that you have velocity in units of pixels per second, and then as we go, I'll show you why it doesn't matter that it's in pixels per second. In a moment, after we finish this calculation, I'll make some notes about how we might estimate the velocity of the object in units of pixels per second. But for now, let's assume that we have this estimation. Now, I'm also going to make another estimation. This is the size of the object in units of pixels. I'll call that d. We'll finish this derivation, and then I'll give you an example to help you understand what each of these values means and how we might get it. Now, our brightest image of the motion, which is also the smallest distance that the object moves, would be obtained if the object moved d pixels in delta t number of seconds. Since I don't get to control the velocity of the object, I only get to control delta t, I'll set this equal to v, pixels per second. And so we can calculate delta t simply. Delta t in units of seconds should be set equal to, and here I'm going to use the approximation symbol, should be set approximately equal to d in units of pixels divided by v in units of pixels per second. Let's take a look at an example. Let's suppose that I have a camera set up looking at a road. And suppose that I want to detect the motion of cars driving along this road. In order to calculate a good value of delta t, I need to estimate d, the size of a car, in pixels, and v, the approximate speed of cars on this road, in units of pixels per second. In order to get both of these things, I just need one value. This one value is a conversion between pixel units and physical units. I'll set up my camera in the position it will be detecting these cars on the road, and then I'll walk away from the camera, the same distance that cars would typically be from the camera. I'll then measure the distance from the leftmost point that my camera can see to the rightmost point that my camera can see. Let's call that value W. W will be in units of meters. Now, I know the resolution of the pictures that I'm taking with my camera. Let's suppose that the resolution of these pictures is 640 by 480. That means that in the left to right direction, we have 640 pixels. Here, that gives me a conversion factor of W meters per 640 pixels. I know that the length of an average car is about 4.5 meters, but I need to get that value in pixels. So D, which is in units of pixels, is equal to 4.5 meters, the average length of the car, times 640 divided by W. This is pixels per meter. The meters will cancel out and leave me with the length of an average car in units of pixels for this particular example with this example camera setup. Next, I need to have the average V. V, remember, is in units of pixels per second. This doesn't have to be exact. In other words, if a car is driving above or below the speed limit, we probably won't miss it if we assume a V of being the speed limit. However, this does do a good job of helping the camera to ignore input that is not relevant. For example, the speed of a pedestrian walking along the street is much less than the speed of the car driving, and so setting up my delta t with this V assumed will help to allow us to ignore pedestrians. So let's suppose that the speed limit on this road is 45 miles per hour, which is equivalent to about 20 meters per second. I can use the same conversion factor I used before to convert this to pixels. Now let's calculate delta t as d over v. Now notice that in this calculation, the conversion factor actually cancels out. And so we can actually calculate delta t also in meters units or any other units as long as the numerator and the denominator agree in the length units. Let's go ahead and implement this in our Python code. I have here the color subtraction code that we've written previously. So that we don't lose this code, let's go click on File and then Save As, and save this code as a different name. I'm going to call it Motion. In this color subtraction code that we already have, we only take one image and show it on the screen. In order to do motion detection by difference, I need to take one image, wait an amount of time t, and then take another image. So I'm going to start by going in here to my frame things and change all of these variables to 1 to mean that this is the first image that we've taken. You'll also need to change these variables here to say red 1, green 1, blue 1, and I'll notice that in a minute and make that change. For now, the next thing that we need to do after taking this image is wait an amount of time. In order to do that in Python, we need to import another package that's called time. Then we can use the function time.sleep. In parentheses, we put the number of seconds that we want to wait. I'm going to set this equal to 0.1 or 1/10 of a second for now. Now copy all of this code where we're taking another image and paste it after the sleep. Then change all of these 1s to 2s because this is the second image that we've taken. So up here, I'm going to put the 1 into all of these. These are also 2s. Now the next step is to take one of these images and subtract it from the other. I'm going to use the red only image as the image that we'll subtract because I'm going to have you test it by just waving your hand in front of the camera, and the camera tends to pick up human skin as a red color. So that's why we're going to use red only as our grayscale image. So red only, the difference is equal to red only 2 minus red only 1. Let's rename this difference image so that we remember what it is. Instead of red only, I'm going to call this image motion. This will be our image of the motion. Now we can also calculate the location that the motion is happening by adding in motion to this column sums. Then we also have to change this thing here into motion. Then let's scroll down a bit and clean up the plots that we have. We still want to show the frame, but now the second thing we'll show is motion. For now, let's comment out the rest of these lines. Now, before we go ahead and run this code, we need to add in the lines that format our output correctly. We need to make sure that the output only has values between 0 and 255. And we have to make sure that the motion image is just an unsigned 8-bit integer. So in this line here, we'll make motion equal to uint8 motion. Then come up here to where we're limiting the red only image to be between 0 and 255. Take these two lines of code and copy them. Then paste them after we calculate the motion image. We want to limit the motion matrix to be between 0 and 255, the same way we're doing it for the red only image. Okay, now go ahead and run the code. It should be that the position output to the screen here is 0 when nothing is moving. Wave your hand around in front of the screen like I'm doing here. You should see the position of the motion from left to right being displayed here in your shell. When you wave your hand near the left-hand side of the screen, the number becomes small, and when you wave your hand by the right-hand side of the screen, the number becomes large. Play around with this a little bit, and now we're going to do a little experiment. Try this. While your code is running, wave your hand just starting from the left-hand side of the screen to the right-hand side of the screen, and watch how the numbers respond. Try to note the distance of your hand from the camera and try to pay attention to how fast your hand is moving. Make some observations about how well the numbers indicating the position of your hand from the left to the right of the screen follow your motion. Then go back to your code. Let's make one change. Find the line of code where we're doing the delay. This is the delta t value. Change this value to a larger number, like 0.5. Then run the code again. Do the same experiment. Try to hold your hand at roughly the same distance from the camera and move your hand in a smooth motion from the left of the screen to the right of the screen. And watch how the numbers respond. What differences can you see in how well the numbers follow the position of your hand? Also, try a second experiment. Put your hand in view of the camera and hold still. Try to note how easy or difficult it is for you to hold still and disappear to the camera. Note that disappearing to the camera means that the number output in the shell is 0, even though your hand is not fully to the left of the screen. In other words, if your hand is in the view of the camera, but the number output to the shell is 0, then that means that you're holding still well enough to disappear. Try to take note of how easy or difficult it is to disappear with the delta t set at 0.1 versus 0.5. Then let's try another value. Let's make the delta t much smaller, like 0.01. Then run the code again and do the same experiments. Hold your hand at the same distance from the camera and move smoothly from the left of the screen to the right of the screen. How well does the number follow the position of your hand? Then put your hand in view of the camera and hold still. How easy or difficult is it to disappear with the delta t at this value? After you've done these experiments, try to draw some conclusions about how you might determine a good value of delta t. Next, let's take a look at the optical flow method. I noted earlier that the optical flow method is similar to masking. In fact, optical flow is nothing more than the application of a mask that stretches over the new dimension of time in our images. If you remember from what we learned about masking, you know that we often apply a mask that is a 3x3 mask. A 3x3 mask allows us to determine things about the image by comparing one pixel to the pixels that are adjacent to it in each direction. In optical flow, we're going to use this same approach, except instead of using only the dimensions of the X position and the Y position of the pixel, we're going to add in the dimension of time. In order to do this, we need to start by having 3 images. These 3 images will have been captured at 3 different times. So what this box here represents one complete image, and I'll say that it was captured at time t1. Then there's a second image that's captured later in time, and we'll call that image the image captured at time t2. And finally, we have a third image captured at time t3. I'm trying to show these 3 images as being stacked on top of each other. If these 3 images, if we can picture them as being stacked on top of each other, it will help us to understand how we apply the mask. Just like we would apply a 3x3 mask to a single image, we can apply a 3x3x3 mask to 3 images taken in time to get a 3-dimensional mask where one of our dimensions is time. The mask that we apply in the optical flow method looks like this. the mask that is applied to image T1 is what I'm showing right here. Then, stacked on top of this image, this is the mask applied to T1. We have a second mask applied to T2. The mask applied to T2 is all zeros. Then we have a mask applied to T3. This mask is the same as the mask applied to T1, except all of the numbers are negative. These three masks can be used to find the gradient of an image. That is, how much is the image changing from one pixel to another. In the optical flow method, we apply this 3 by 3 by 3 mask in the time direction, and we also will take this 3 by 3 by 3 mask and rotate it 90 degrees in order to apply it in the X direction and apply it in the Y direction. In other words, we apply this mask in all three of the dimensions that we're looking at, the X, the Y, and the time dimension. By applying the mask in all three dimensions, we can back out how much of the change in the image is due to changing in time versus how much change in the image is due to changes or gradients in the image in the X and Y directions. By combining these three pieces of information, the change in X, the change in Y, and the change in time, we can actually get the velocity in X and the velocity in Y. Let me show you how those equations work out. I'm going to use a little bit of notation here, so I'm going to start out by introducing you to the notation I'm going to use. If we apply the mask, that 3 by 3 by 3 mask, in the X direction to pixel number 1, this is how I'll represent that result, mx pixel 1. Now, when we apply the optical flow method, we generally don't apply it to an entire image all at once. Instead, we'll take our image and we'll split our image into smaller areas. So this may be one image split up into areas. Each of these areas has a number of pixels inside of it. So one of these pixels inside the area, this will be pixel 1, the next pixel will be pixel 2, and so forth. Now, I'm going to create a matrix called A. And this matrix A is the result of the mask applied in the X direction to pixel 1, the result of the mask applied in the X direction to pixel 2, and so forth all the way down until we have the mask applied in the X direction to the last pixel within this one little image area. That makes up the first column of the A matrix. The second column of the A matrix is the result of the mask applied in the Y direction to pixel 1, the result of the mask applied in the Y direction to pixel 2, so on and so forth until the mask is applied in the Y direction to pixel N. I also need a second vector, which I'll call B. B is the result of the mask, actually the negative of the result of the mask. Let me shrink this because it may be getting off the page here. Applied in the time direction to pixel 1. The opposite of the result of the mask applied in the time direction to pixel 2. So on and so forth until we get to the mask applied in the time direction to pixel N. Now that I have the A matrix and the B vector, all we have to do to find the velocity of this image piece in the X and Y directions is to solve a matrix equation. I'll say that the vector V is equal to the velocity in the X direction and the velocity in the Y direction. And we can solve for the velocity by using the matrix equation that I'm sure you're already very familiar with, AV equals B. Now this equation, as you can probably see from these equations that I've written here, has more equations than it has unknowns. There are a number of different algorithms that you can use to solve this, and in lab I'm going to be showing you how to use an algorithm to solve this. We'll be using a method that's known as the Lucas-Kinnaid, which is spelled like this. We're not going to write any code to do optical flow, but I'm going to give you some example code that you can play around with. If you're watching this video on robogrok.com, there's a text box next to this video with my optical flow code pasted in it. Highlight all of that code in the text box, copy it, and then paste it into a new file window in Python idle. Run the code and test it.